Welcome to Quantum Leaps, the podcast that explores the bleeding edge of technology. Today, we're diving deep into a topic that's been buzzing in the scientific community for years, but is now stepping firmly into the realm of practical reality: quantum computing. For a long time, quantum computing felt like something out of a sci-fi movie: complex theories, mind-bending physics, and promises of unimaginable power. But as we move through 2025 and into 2026, the landscape is shifting dramatically. We're moving beyond mere speculation towards fault-tolerant systems and real-world industrial utility. It's a revolution, bypassing the traditional limits of silicon-based transistors by harnessing the wild, counterintuitive principles of quantum mechanics. This isn't just about faster computers. It's about a complete reimagining of how information is processed. We'll explore the economic impact, the groundbreaking technologies, how these machines actually work, and the exciting and sometimes daunting applications they're already finding. Let's start with the big picture: the macroeconomic and geopolitical landscape of the quantum era. Financial commitment to quantum technology has reached a critical mass. We're seeing a clear transition from venture-backed experiments to institutional-scale deployment. By late 2025, the global quantum computing market was valued between $1.8 billion and $3.5 billion, with projections soaring to $5.3 billion by 2029. Some models even suggest a staggering $20.2 billion by 2030, marking a compound annual growth rate of nearly 42%. This isn't just numbers. It shows a fundamental shift in how capital is being deployed. In 2024, venture capital funding for quantum startups topped $2 billion, a 50% increase over the previous year, and then it doubled again in the first 3 quarters of 2025. Governments worldwide are also recognizing quantum computing as a cornerstone of national security and economic sovereignty. Now for the scientific paradigm shift itself, moving from classical bits to quantum qubits. At its core, this revolution departs from the binary logic of traditional computers. Classical computers process information using bits, which are always in one of two distinct states, 0 or 1. Quantum computing, however, uses qubits. These operate under the laws of quantum mechanics, specifically superposition, entanglement, and interference. Think of it like this: superposition allows a qubit to exist in a combination of both 0 and 1 states simultaneously. It's not just 0 or 1. It's a blend of both until measured. This enables a quantum computer to store and process a vast amount of information all at once. While n classical bits can represent only one of 2 to the power of n configurations, n qubits in superposition can represent all 2 to the power of n configurations at the same time. That's an exponential leap in information processing. Then there's entanglement. This is perhaps the most distinctive feature. When qubits become entangled, their quantum states are intrinsically linked. The state of one qubit cannot be described independently of the others, even if they're physically separated by vast distances. A measurement on one instantly influences the outcome of its entangled partner. This non-local correlation is what gives quantum computers their exponential parallelism, allowing operations on an entangled system to affect the entire state space simultaneously. Finally, interference is the computational tool. Quantum algorithms don't just try every answer. They use interference to navigate towards the correct solution. By manipulating the phases of qubit amplitudes, an algorithm can amplify the probability of the correct answer through constructive interference and cancel out incorrect ones through destructive interference. It's like waves in a pool. They can combine to form a bigger wave or cancel each other out. This means quantum computing is probabilistic and parallel, using linear algebra compared to classical computers, which are deterministic and use Boolean algebra. One of the most defining characteristics of 2025-2026 is the fierce competition between several distinct hardware modalities. Unlike the early days of classical computing, which quickly settled on silicon transistors, the quantum industry is exploring multiple ways to build a qubit. Each approach has unique advantages and significant engineering hurdles. Let's break down the main contenders. Superconducting circuits. These are championed by giants like IBM, Google, and OGS. They use loops of superconducting material cooled to near absolute zero. We're talking millikelvin temperatures, colder than outer space. They exploit the Josephson effect to create artificial atoms that act as qubits. Pros: they currently lead in raw physical qubit counts. IBM's Condor has over 1,100 qubits and offer high gate speeds. Cons: They have the shortest coherence times, how long a qubit stays stable, and require massive power-hungry dilution refrigerators. As qubit counts grow, wiring complexity and interference, crosstalk become major barriers. Trapped ions, led by quantinuum and IonQ. These systems use individual charged atoms ions as qubits, suspended in vacuum chambers by electromagnetic fields and manipulated with lasers. Pros: they are the fidelity benchmark, meaning they achieve extremely high accuracy. Quantinuum's H2 processor boasts 99.87% 2-qubit gate fidelity. They also offer exceptionally long coherence times minutes, not microseconds, and high connectivity, meaning any qubit can interact with any other. Cons: the trade-off is speed. Trapped ion gate operations are much slower than superconducting gates. A computation taking 20 hours on a superconducting processor might take 10 years on a trapped ion system. Scaling large chains of ions is also a challenge. Neutral atom arrays, pioneered by Cura and Pascal. This approach uses optical tweezers-focused laser beams to trap and arrange individual atoms. Pros: they can scale to thousands of qubit. Systems already exceed 1,000 atoms and operate at room temperature, within a vacuum chamber, eliminating the need for extreme cryogenics. They're well suited for analog quantum simulation. Cons: gate fidelities are currently slightly lower than trapped ions, around 99.5%, and the ability to dynamically rearrange qubits is a key feature. Photonic quantum computing. Developed by PsiQuantum and Xanadu, this encodes qubits in light particles photons. Pros: photons are naturally resistant to decoherence and can travel through fiber optic networks at the speed of light, making them ideal for distributed quantum computing and communication. They are modular and can potentially operate at room temperature. Cons: the primary difficulty is that photons don't like to interact with each other, making 2-qubit gates hard. Current systems often rely on probabilistic measurement-based quantum computing, requiring many ancillary photons. Silicon spin qubits. Intel is leading the charge here, storing information in the spin of an electron within a silicon quantum dot. Pros: this approach leverages the same manufacturing techniques and infrastructure used to build modern computer processors, potentially making scaling much easier and cost-effective. Intel's Tunnel Falls chip, a 12-qubit device, demonstrates 95% yield on 300mm wafers. Silicon qubits are also far smaller, meaning millions could theoretically fit on a single chip. Cons: natural silicon contains isotopes that interfere with coherence, requiring purification or other workarounds. So, who's winning this race? It's not clear yet. Superconducting circuits lead in raw performance, trapped ions in fidelity, silicon in manufacturability, and photons in networking. Each has its strengths, making it anyone's game. Building a useful quantum computer isn't just about making qubits, it's about making them reliable. This brings us to error correction and the rise of hybrid systems. Quantum states are incredibly fragile, and even the slightest interaction with the environment can cause errors. This is why fault-tolerant quantum computing, or FTQC, is the holy grail. The industry is moving from simply counting physical qubits to creating logical qubits, units of information encoded across many physical qubits, to detect and correct errors. In a historic milestone in 2025, several hardware platforms showed that logical qubits could outperform the physical qubits they were made from. Google's Willow chip, with 105 superconducting qubits, achieved below-threshold error rates, meaning adding more qubits reduced the overall error rate exponentially. This is fundamental for building a scalable, reliable quantum computer. While the surface code has been the gold standard for error correction, it requires massive overhead. However, new quantum low-density parity check (QLDPC) codes emerged in 2025, promising to reduce qubit overhead by up to 90%, potentially accelerating large-scale fault tolerance. Microsoft is pursuing an ambitious project with topological qubits, exemplified by their Majorana 1 chip. These qubits store information in the global configuration of a system, making them inherently resistant to local environmental noise. It's a high-risk, high-reward approach that could offer revolutionary stability. Intel is also uniquely positioned with its cryo-CMOS revolution. They are leveraging industrial semiconductor manufacturing to integrate silicon spin qubits with cryogenic control electronics. Their host-switch chips place control electronics directly inside the refrigerator, solving the wiring hell of thousands of cables needed to control qubits. Crucially, the industry has largely abandoned the idea of a standalone quantum computer. The focus is now on quantum-centric supercomputing (QCSC), where the quantum processing unit QPU acts as an accelerator for classical supercomputers, handling subroutines that are too complex for classical chips. This integration isn't just a software challenge. It requires fundamental hardware to achieve the ultra-low latency needed for real-time error correction. In March 2025, NVIDIA and Quantum Machines introduced the DGX Quantum, the first system to tightly couple a GPU-CPU superchip with a quantum controller. This setup achieved a round-trip latency of less than 4 microseconds, over 1,000 times faster than previous attempts. This ultra-low latency allows classical AI and reinforcement learning agents to continuously calibrate and correct the QPU in real time, effectively learning the noise environment to improve fidelity. So, what can these incredible machines do? By 2025, the narrative of quantum computing shifted from what could it do to what is it doing. Industries are already seeing early signs of quantum utility. Finance. JP Morgan Chase, in collaboration with IBM, has used the quantum approximate optimization algorithm QOA to optimize portfolios with hundreds of assets, reducing computational time from days to mere hours. Goldman Sachs is also exploring quantum machine learning for fraud detection, aiming for a 30 to 50% improvement in accuracy over traditional AI models. Pharmaceuticals. This sector is a natural fit, dealing with molecules and proteins governed by quantum mechanics. Companies like Roche, IBM, and AstraZeneca are collaborating on molecular simulations to predict drug binding affinities. IonQ even announced a breakthrough in accurately computing atomic-level forces, crucial for modeling carbon capture. Materials Science, BASF, and Covestro are investing heavily in accelerating chemical R&D. The UK's NQCC has conducted studies on offshore wind farm modeling and metal corrosion, mapping a clear path to deployment. Finally, we can't talk about quantum computing without mentioning its double-edged sword, the quantum threat. A powerful quantum computer, using Shor's algorithm, could break current encryption like RSA and ECC, which secure our digital infrastructure. To counter this, NIST released the first finalized standards for Post-Quantum Cryptography (PQC) in 2024 and 2025. These new algorithms are designed to be resistant to both classical and quantum attacks. Security agencies are warning about harvest now, decrypt later, where adversaries collect encrypted data today to decrypt it later once quantum computers are available. This has made PQC readiness a top priority for 2026, with the US NSA planning a full switch by the early to mid-2030s. As we look towards 2030, the path ahead for quantum computing is becoming clearer. The 2025 to 2026 period marks a significant shift. Quantum computing has transitioned from a physics project to an engineering discipline. The demonstration of below-threshold error correction and the deployment of hybrid platforms like NVIDIA Quantum have provided a clear path toward large-scale fault tolerance. The industry roadmaps are focused on 4 key areas: logical qubit growth, scaling from the current 10 to 30 logical qubits to 100 in 2026, and eventually thousands by the early 2030s. Quantum-centric supercomputing, fully integrating QPUs into data centers as standard components of high-performance computing clusters. Widespread industrial value, developing specialized applications that offer a clear strategic advantage over classical-only methods. Hardware consolidation. By the end of 2026, the intense modalities race will likely narrow, as some architectures prove more scalable and robust. The quantum revolution isn't just on the horizon, it has arrived. The focus has shifted from can we build a qubit to can we build a system? And the answer, from the labs of IBM, Google, Microsoft, and Intel is a resounding yes. The future involves meticulous engineering, full-stack software development, and a global transition to a quantum-secure future where quantum and classical systems work together, not as replacements, but as powerful coprocessors, unlocking unprecedented possibilities. Join us next time as we continue to explore the fascinating world of groundbreaking technology.